Ready? Look at all the objectives we've got. Look at all the objectives. Okay, quiet, please. So we learned about compositions a couple sections ago so that we would understand inverses. And then we learned about inverses so that we could understand that radical functions should be the inverses of quadratic functions. And now that we know that, this last section is actually about the graphs of radical functions. So we should expect, kind of like we just saw in these two here, the last two homework problems, that the graphs of radical functions are flips of parabolas across the line y equals x. Specifically, like that. Okay. So here's the right half of a parabola. If you flip it across the line y equals x, you get that. And that is the square root function. Y equals the square root of x. Right? Again, notice the way that I wrote this one up here. It's just the right half of it. So I've got a domain statement. X is greater than or equal to 0. That describes just that half of a parabola. Right? So here's the parent function. Right? Most of what we're doing today is just moving it around like we've already done with absolute values and quadratics. It's all very familiar and goes very quickly. But we should mention, especially in this class, we should mention domain and range. Because it's something that gives us trouble, and this is really where it just starts to be presented. Okay, again, so what do we expect would be the domain of the square root function? What can I plug in the square root? Greater than or equal to 0, right? So x greater than or equal to 0. And the range is, since you assume it's positive, y is greater than or equal to 0. And that should be obvious from this, right? You should be able to look at a graph and tell the domain and range, right? If the graph starts at 0, 0, and only goes up and to the right, then the domain is x greater than or equal to 0. The range is y greater than or equal to 0. Right? If you get comfortable looking at a graph like that, that makes things a lot easier. Because a lot of times you can just tell, look at the graph. You can tell the domain and range. Do you have a question, Adam? Okay. Okay, so now that we know what the shape of the parent function is, we're going to figure out how is it that we can graph using the transformational approach by understanding what happens to the graph when we add and subtract numbers inside and outside the function. And it'll work the same way that it has already for absolute value and quadratics. What normally happens to the graph when you subtract inside the function? Nothing? Try again. Try again. It goes right. Minus inside means right. Okay, and how about a plus after the function? Up, down, left, or right? That's a up, right? Okay, how about a minus in front of the function? Morgan? It flips it. Flips. Okay, how about a plus when it's inside? Left. Okay, how about a minus when it's outside? Down. So that should just be kind of review, because that's how it worked with the others. And it works the same way. Right? It's kind of like conjugating a verb in Spanish or whatever language you take. You know, you don't learn all new rules for every verb. It works the same for every one. Okay, so let's see. What kind of shift do we expect to see here? Up to. A plus after means up. So that's up to. So you would just start. We're not plotting points here. We're just taking this, which is the graph of the parent function, move it up to. So start it, instead of starting at 0, 0, start it here and draw something that has that general shape. Done. How about that one? Down 3, right? Down. Right. So instead of starting at 0, 0, start it at 0, -3, and then go up and to the right. Okay, here's your first U try. Put all 4 of these on the same background, right? Graph all on one graph, just hand draw it. Graph those 4. Right, these are the U tries. You're gonna hand them in, and all I'm looking for is that you've done it. If you're not doing them, you're not going to get all the credit for it. I think you'll end up with like 4 or 5 graphs today.
Should we try doing them in different colors like you did? Or like you...
Any way you want. I mean, I doubt everybody has 4 colors they can go to. So what was the first one? Up, down, left, or right? Up, which meant we went from just go up 1, right, the y-intercept, up. If the next was in red, what is the next one? Down. Man, this thing. Down. So down 2, started right there, and go up and to the left. And the next one is a what? Looks like it's down 4. Down. So started at -4 on the y-axis, and the last one in our favorite color here, up 5. Started at 5 and go. Pew. Easy? Too easy? Oh man, let's start doing something harder. Okay, what's the shift here? Left, right? That means left. So 1, 2, 3, 4, and make the basic shape up and to the right. Nope. Just showing. How about this one? That is right. So go over 1 and to the right. Okay, here's your turn. Do that. Another graph. Start another graph. Put all 4 on the same background. So what kind of shift is the first one? Right. Right, left, left, and right. I mean, you got to get straight on this. When it's inside, it's like the difference between a linear factor and a zero, right? If the zero is 2, the linear factor is x minus 2, right? It's the same reason this has that same kind of opposite feel to it. So let's see. Right 3 would mean go to 3 to the right and kind of repeat the shape. This is going to be 1 to the left. Repeat the shape. Oh, I wanted to change colors on that. That was a 1 to the left? Yeah. Right, then the next one was a 6 to the left. And it did that again. 6 to the left. And the last one is 4 to the right. So far, so good? Okay, do you remember what we called it when you multiply a function by a number? It's a stretch, right? Well, if you multiply it by a number that's bigger than 1, it stretches the graph. If you multiply it by a number which is less than 1, compression. So the easiest thing to do for something like this is make a quick table of values to give you, where do you want to draw this thing. I mean, it's because it's multiplied by 2. It's going to go up faster than the parent function did. And if I do a table of values, first I got to put some x values in that table. Which x values would make the calculations easiest here? 0, 1, and what? Not 2. Because then I'd have to plug in the square root of 2 as a decimal. I don't want it. How about 4? Now negative 1, it's not in the domain, right? But you could put in 4, and that'll make the calculation easier, right? So what the y for x equals 0, y equals 0. For x equals 1, y equals 2. For x equals 4, y equals 4. So just with those 3 points, right, I can go 0, 0, 1, 2, and 4, 4. And then connect those up with a smooth, continuous line. Boom. So it's going up faster than the parent function. And that, again, is called a stretch. Good on that? Then you try another graph, try to do the same for y equals 3 times the square root of x. What did you get for y values? 0. When x equals 1, what does y equal? 3. And then when x equals 4, Square root of 4 is 2. 3 times 2 is 6. Right, so those would be your values. 0, 0, 1, 3, 4, somewhere up there. Connect them with a smooth, continuous line. Easy stuff. So far, so good. Now, sketch. Okay, what two things are going on in this one? Yeah, the minus in front is going to make it go downwards, right? Instead of up and to the right, it's going to go down and to the right. Flip. And the minus 1 after means shift the whole thing down 1. So I'm going to start it here, down 1, and it should be about there. It should be about there. Yeah.
How do we know when it means down or when it means right? Is that going to go minus right?
Okay. You got to have more attention to detail than that, right? Right? Like if it's minus inside, that means right. If you look at ours, that's after the radical. Again, it's a difference between it being inside the function or outside the function. Okay? So try to do this one. Another you try. You get a chance to do it right there, Josh. Did everybody get those? It's the right shifts? Okay, so go to the right one, and then it should look something like, about like that. Now, most of the time, this chapter is about radicals. It's not just about square roots. But most of the time when you see the graph, they're square roots. If there's an exception to that, maybe it'll be a cubed root, right? And a cubed root has its own particular graph, which unfortunately, I make these with a thing called GeoGebra, right? You can download it for free on the internet. It's pretty good, but it wouldn't. When I did the cubed root, it was only drawn like I put a domain in there of x greater than or equal to 0, and I didn't. So I had to go to the calculator and do a screen capture like that. Doesn't look very good, but the x to the third, the cubic, looks like this. So we would expect the inverse, which is the cubed root, to be a flip of that across the line y equals x. Okay? I mean, this is hard to see because of the axes and everything there, but this thing has just a little bit of a wiggle right there in the middle. Remember, we expect that a cubic could have 2 turning points. You could have 1 less turning point than the degree. Since it's third degree, it should have like 2 turning points in it, and it kind of does, but it's like really concentrated in there around the origin. Now, when I flip it, maybe you can see them a little bit better, right? It turns, and then it turns again, and it goes this way. So when you do a transformation of this, I mean, it's the same thing. This would be the parent function, and you use the transformations the same way. Right, there's the parent function of the cubed root. Okay, and what shifts are we going to put on this thing? Left 2, down 1. Now, you can do that, take a few points. Just point for point. Just move them left 2 and down 1. For example, the origin, we got the point 0, 0 on the parent function, so go left 2, down 1, right? It'll be there. How about we had the point 1, 1 on the parent function. We'll go left 2, down 1. We had the point -1, -1. So we'll go left 2, down 1. And then maybe use these as a guide. We're trying to make a shape that looks something like this. So does it look close enough for government work, as they say? Yeah. So try to do one for yourself. And that one, it may be hard to see, but there is a minus in front of it too. And I imagine it'll be kind of hard to see how are you going to move it in both those directions and flip it, and then what is it going to look like. But you're creative, right? Got the creativity of youth. Rebecca goes. I'm going to do this. Okay. Kind of wiggly. That's my flip. Now, let's see if I can do this. Go, go. Okay, there we go. Okay, now I'm going to go left 3, and then I'm going to go down 1. How's that? Something like that? Pretty wiggly line. But it's got to be left 3, down 1, and then flipped. One time on the benchmark, which they make downtown, you know, they had a graph like this on it. And they said, what kind of function is it? And of the 4 choices, none of them said cube root. They had one that said cubic, but that's not a cubic function. It's a mistake. Clear as mud? Are we ready? Are we ready? Yeah. That's it. I do know we're not. Yeah. All the rest of these are blank. They're all blank. Okay. And besides that, the homework is what you just did. So just turn that in, and that's your homework. The U tries were these problems right here. You already did it. Okay.